Hello everyone, and welcome to the webinar one for BIOB111 chemistry biochemistry. So we'll just pausing a little bit to wait for a few more attendees to come on, but we'll get started pretty quick. Just make sure everyone can see what I'm seeing. Yep, beautiful. So just while we're waiting for some more people to come along, you're obviously all in listen only mode. If you want to ask any questions, there's a little questions button down the side, or there's like a chat button, so feel free to just type in anything you want to talk about, or any questions or anything like that, and yeah, and I can answer them. But as always, if you have other questions or you want to talk about things in more detail, then I'm always available afterwards to arrange a one-on-one chat with. All right, might get underway. So, as we said, chemistry, biochemistry, this is webinar 1. So in this webinar, we're going to be covering the first 4 weeks of material. Now, your quiz is now up this week, as you probably are aware. It went up Monday morning and it will be open until Sunday night, so 11:55 p.m. this Sunday. It's a 40-minute quiz, so you just log on when you're ready to do it. You sit down and you do it as best as you can, and you can do it anytime in the next few days. So the quiz is going to cover content from weeks 1 to 3, so sessions 1 till 6. But we do cover a little bit of the week 4 material in this webinar, but that's not going to be in the quiz this week. Okay, so a little bit about me. So my name is Taben and I'm a nutritionist. So I studied at Endeavour quite a few years ago. I've worked in industry, in research and development of supplements and in compliance of supplements for a long time. I also practice, so I mainly practice as a sports nutritionist and help out with like sort of family nutrition, that sort of thing as well. Throughout my time, particularly in product development, I did rely on a lot of understanding of chemistry to figure out sort of weights of different ingredients and that sort of thing. So chemistry was always very useful to me, and certainly in practice, being able to understand chemistry and biochemistry does really inform your understanding of the treatments that you're giving, whether that be dietary or supplements or even lifestyle. So yeah, so I've used chemistry, biochemistry a fair bit throughout my career. So it's definitely good. So if you're ever thinking that you're learning something that's not going to be useful to you, it will be useful. All right, so lots of information so far. Just in the last few weeks, we've gone from, what is matter to acids and bases and electronegativity and all the rest of it. So we've covered a lot of ground. So if you are feeling a little bit overloaded, reach out for help. We're always here to help. But certainly doing the tutorial questions and the practice quizzes, the quiz one that you're going to be assessed on this week, the tutorial questions are a really good guide to the kinds of questions you can expect there. So do those, and if you're having any trouble getting one right, you just don't understand why you're getting it wrong, just message me or post on the LMS and we can talk you through it so that you can understand. All right, so the periodic table of elements. So we covered this a little bit in week 1. The periodic table of elements lays out all the different atoms, and it lays it out in a way that enables us to predict the chemical and the physical properties of the atoms. So it's a really useful table. In particular, we are really interested in what are termed the representative elements, which are these ones here and these ones here, and also the noble gases, which are here. Now, the reason that we're quite interested in these ones is that the group number, which is that 2A or 3A, etc., tell us the number of sort of valence electrons that any atom within those, any atom within that group has. So when we get into ionic bonding and we talk a little bit about that sort of thing in a moment, we're going to see that we refer back to that group number. It's actually a really quick and easy way that if you're trying to find out, how many valence electrons fluorine has, well, you just look to the group number. It's 7A, so it has 7 valence electrons. So it's really useful in that way. The other useful distinction in the periodic table for this subject that's kind of coming out is the metals versus non-metals distinction. So you can see here in the front of your Stoker textbook, you actually have a diagram that basically it puts a big heavy line down there, and it just goes all the way down. And this side are all metals, and this side are all non-metals, except of course for hydrogen, which is also a non-metal. And we'll see that's important because ionic bonding occurs between a metal and a non-metal, whereas covalent bonding occurs between two non-metals. So if we have a compound and we're not sure whether it's covalently bonded or ionically bonded, then we can just have a look and see, is one of the compounds, a metal? If it is, is it zinc and say oxygen bound together? Well, that's probably an ion because that's zinc is a metal and oxygen is a non-metal. Whereas if it's carbon and hydrogen bonded together, well, that must be covalently bonded because they're both non-metals. So yeah, so just a couple of points there, just pointing out that the representative elements, so this group here and this group here in the noble gases, we can actually use the group number to tell us how many valence electrons that they have. And also the metal versus non-metal line in the periodic table, which kind of runs down. And in your textbook, you've got a big dark jagged line there. So it's quite useful for that. Clear that. All right, so the different things that we've covered so far. In week 1, obviously we've got an introduction to matter and we started to look at chemical bonding. In week 2, we looked at chemical reactions, reaction rates and balancing reactions, chemical equilibrium. In week 3, we looked at the different states of matter like solutions and liquids and gases and acids and bases. And this week we're starting to get into organic chemistry. So weeks 1 to 3 was sort of our chemistry. Now we're getting into organic chemistry, and then eventually you're going to get into biochemistry. So you can see that it's starting to build on itself. Okay, so some of the topics that we're going to cover today, atomic number and atomic mass. So it's very important to look at, and we'll have a look at what we mean by those terms in a moment. Electron configurations we'll look at, molar mass we'll look at, and also balancing equations. So I know that probably for a lot of you, balancing equations is one of the sort of the trickier ones, and I remember learning it. It was very tricky. So, it's just a practice thing, but I'll give you some tips in a moment for it. Okay, so structure of an atom. All right, so here we've got, get my drawing pen out. Here we've got a carbon-12 atom, or how we would depict carbon-12. So if we just have a look at the general structure of an atom, in the middle here we have our nucleus, and our nucleus has our protons and our neutrons in it. And then outside the nucleus we have our electron cloud, which is all this area where our electrons circulate. Now, atoms will always have the same number of protons and electrons. The electrons can change, as we'll see, as they get oxidized or reduced. The neutrons, however, can be different. So here we've got carbon-12. So what does the 6 mean? So the 6 is the atomic number, and the atomic number refers to how many protons the atom has. Now, what does the 12 mean? Well, the 12 is the atomic mass, and atomic mass is the protons. Say atomic mass. I'll just call it AM. Atomic mass is the same, equals protons, the P, plus the neutrons. So atomic mass is protons plus neutrons. So if the atomic number is 6, that tells us there's 6 protons. The atomic mass is 12, so there must be 6 neutrons in there as well. Now, you'll see that the this is just one of many isotopes of carbon. So an isotope is all the different types of an atom which share different numbers of neutrons. So carbon doesn't always have to have 6 neutrons in it. It could have 5, or it could have 7 neutrons in it, and then that will obviously adjust the atomic mass. If 6 plus 5 is obviously different to 6 plus 6, which is different to 6 plus 7. And then what we find is that in the periodic table, the atomic mass is actually represented down sort of here. That's atomic mass is given, and those numbers aren't whole numbers, because what happens is that they average out all the isotopes. So you might find that zinc has some of them have 30 protons and 30 neutrons, because this is the atomic number, so that's telling us that there's 30 protons in there. So some would have 30 protons, 30 neutrons, and other ones might have 30 protons, 35 neutrons, and other ones, might have 30 protons, 31 neutrons, and then you sort of average out all the weight of all the different isotopes, and you get to a number like 65.39. So what is the charge of each subatomic particle? So protons carry a positive charge, electrons carry a negative charge, and neutrons carry no charge. And we'll see that becomes important when we're talking about ionic bonds and electronegativity, because when we remove an electron or we add an electron, the atom becomes more or less positive or negative. And where are the locations? Well, we've been through that. So protons, neutrons are in the atom's nucleus. Electrons exist in the shells. And one thing about the electrons is that they're always moving. They're not static. And so that's why they're kind of drawn as a cloud, because they could be anywhere in there at any point in time. Okay, so if we zoomed in on the electrons, what is an electron shell and how is it made? So we find that certainly as you go up the periodic table, you end up with atoms with quite a few electrons in them. And electrons are never just in any spot in the electron cloud. What we find is that they actually sort of situate themselves in different energy levels and different positions. So your textbook gives a really good analogy, which is like an apartment analogy. So you can imagine if you had a big apartment building, your first level is your shell, and the shell is like the levels of the apartment. The subshell is like the apartments themselves. So you can imagine an apartment has many levels, then each apartment level has many rooms or has many apartments, and then the orbital is the rooms within each apartment. So we've got the apartment has many levels, each level has many apartments, and each apartment has many rooms. So that's what we find. We have lots of shells. Each shell has subshells, and each subshell has several orbitals. So as the electron energy increases, as the shell number increases, so as we go up the shell number, the electron energy gets greater. Then obviously, as we said, within each shell, there are several subshells. We have S, P, D, and F subshells. And then within each S, P, D, and F subshell, we have orbitals. And then each orbital only contains 2 electrons. And this is important because this kind of leads us to a discussion on valence electrons. And valence electrons are those electrons in the outermost shell. And you might recall from the octet rule that the outermost shell should have 8 electrons in it. So if we look at an atom like sodium, so we go sodium, although it might have, it's got 12 protons, so that means it has 12 neutrons, and the way that I told that was just because of the atomic number. So if we go back to the thing here, oh sorry, it has 11, so let me just get my pen out. So sodium has an atomic number of 11, which means it has 11 protons, which means it has to have 11 electrons as well. And when you put the electrons in all the shells and all the subshells, what we end up with is that it actually has an electron. And you might have just seen then that I can tell it has 1 valence electron without working it out because it's in group 1. It's group 1A, which means it has to have 1 valence electron, just like hydrogen, just like lithium, just like potassium. So they all have 1 valence electron. And then we depict it with this Lewis dot structure like this. We say Na and then 1 little dot next to it, which indicates that it has 1 valence electron. That's all I wanted to say there. And just remembering that, actually I'll draw that back up. So when we got Na, we've got 1 valence electron. Now if we compare it actually to another one with we'll pick another atom, so we'll go oxygen. So in this case, we've got oxygen it's in group 6A, so it has 6 valence electrons. So we have oxygen has 6 valence electrons. So the way that we depict that is that we need to look at the fact that orbitals contain 2 electrons, and each orbital fills up with 1 electron at a time. So to draw that, we would have to go 1, 2, 3, 4, 5, 6. So what we can't do is we can't draw it like, we can't say 1, 2, 3, 4, 5, 6. That's not how it fills. It fills, each orbital has 1 electron and then it fills up again. So each orbital contains 2 electrons and it will fill up 1 at a time. So that the correct Lewis structure is actually this. That's just another important thing, because if you draw it like this, I should draw that a little bit better there. You're actually going to get, you're going to predict that it's going to bond a little bit differently than this one. Okay, so the main takeaway there is that electrons have different energy levels and that this ultimately influences the valence electrons that will be available for bonding. All right, so chemical equations and the mole concept. Okay, so chemical equation. So there's a couple of terms here that I just want to point out. So we've got chemical symbols, we have chemical formulas, and we have chemical equations. And so chemical symbol is what you'd find in the periodic table. So that's a symbol for the atom, like cesium there, or oxygen. These are chemical symbols. So the symbol used to depict an atom. The chemical formula is sort of the name given to this whole compound. So a set of chemical symbols showing the elements present in a compound. So that's a chemical formula. That's a chemical formula. And the whole thing is a chemical equation. So we've got chemical symbols are the atoms, chemical formulas are these molecules, and then the chemical equation is the whole thing. So it's just the terms that you sometimes used quite quickly in textbooks and in slides and that sort of thing. So it's just good to have a good, firm understanding of what they mean when they use those different terms. And the beauty of a chemical equation is that it sort of simplifies and makes us able to write what is happening in a very abbreviated way. Because you can imagine that we could say, you know, 2 cesium atoms bound to 1 oxygen react with water, which is 2 hydrogens bound to 1 oxygen, and you could say it in a really long way, but this enables us to sort of really compactly express what is happening. And some things to point out here, these are the reactants. So the reactants are on the left side and the products are on the right side. So the reactants on the left side and products on the right side, on the right side. Clear that. All right, so balancing chemical equations. So, you know, this is, as I said, this is one of the things that we have to do when we're studying chemistry. It's very important because, you know, we have to note that atoms aren't created or destroyed in a chemical reaction. Some might be accidental when it actually occurs, but when we're looking at it from a theory point of view, you know, the atoms are never lost or are never created or destroyed. So in any sort of chemical equation, we want to make sure that there are equal numbers of atoms on the left side and on the right side of the equation. So what we need to do is we need to add the coefficients, which are the numbers in front of the chemical formulas, to make sure that there are the same amount of atoms. Now, we can't play around with these numbers, because if we play around with those numbers, that actually changes the formula itself. You can imagine ClCl is, you know, Cl bound to Cl. We can't just add in another Cl there and make it bind. We're not allowed to do that, because that would change the actual compound itself. So the only area that we can play around with is these numbers in front there. So to do this, what we need to do is the easiest way is to start with the chemical formula or the molecule or the species with the most atoms. So in this case, we've got 2 here, but I'll start on the left. And the reason that we're going to do that is that if we start balancing this chloride molecule over here, then we could end up, it's easier to balance molecules with fewer atoms in it, because if we balance this one, then we actually might find we throw out this one, throughout this one. So it's easier to start out with the molecules with atoms in it. So we'll start there. A good way to think about it as well is to actually count out how many atoms are on each side. So here we've got Na, sodium bromide, so we've got N, so we've got sodium. There's clearly one sodium atom here. There's one bromine atom here. And then chloride or chlorine, we have 2 on this side. And over here we have Na, we have Na1. We have, actually I'll ignore that, I'll write it out. So it's the same on each side. Bromine, we have 2, and chloride, we have 1. So we've got the same number of sodium atoms, which is good. The bromine is different. We've got 1 on this side and 2 on the right side, and we have 2 chlorine atoms and 1 chlorine atom on the right side. So what we want to do is we want to start balancing it. So we say Na, so sodium on the left side here. Do we need to add anything to that? Well, no, we've got 1 sodium atom over here and 1 sodium atom over there. So we're happy with that. Then we go to the next atom in the largest species, which is bromine. And here we've got 1 bromine over here, but 2 over here. So straight away we know we need to increase the number of bromine atoms on this side. So we're going to put a 2 there. And then we say, do we have the right number of bromine? So we've got 2 bromine over here. We've got 2 bromine over here. So yes, so now that has become 2. But we've actually increased sodium over here by 2 as well. So now the sodium is unbalanced. So we've got the sodium is 2 on this side, and sodium is 1 on this side. We've got bromine is 2 on this side, and bromine is 2 on this side. So this one we're happy with. But chloride or chlorine and sodium are still wrong. So we're going to come over to this side, and we're going to choose the biggest molecule again and say, what can we do here? Well, fortunately, we've got 2 chlorine over here and 2 sodium over here. We've got 1 sodium over here and 1 chlorine over here, so we can just add 2 here. And then when we do that, we can count it back up and say sodium, we've got 2, so that's still correct. Bromine, we've got 2, and chlorine, we've got 2. And now we've got sodium, we've got 2. Bromine, we haven't touched, we still have 2. And chlorine, we now have 2. We just check, we've got 2 sodium, 2 sodium, tick. 2 bromine, 2 bromine, tick. 2 chlorine, 2 chlorine, tick. So that's probably the easiest way to go about it, is just to choose the largest molecule first and balance that one. Okay, so put your coefficient in front of the largest molecule first. Don't start by putting coefficients in front of the smaller molecules, because you'll get yourself in a bit of a bind, possibly. So if you start out with the largest species, with the molecule with the most atoms, then it usually comes out a little bit easier. And as I said, the best way to do that is just to do lots and lots and lots and just practice and practice and practice, and then you start to get the hang of it. But if there are any equations that you just can't figure out how to balance, or the tutorial answer, you just can't figure out how they got to that, send the question through to me, and we can talk through how we would balance that, so you can see the process, because that's all it is. It is a bit of process. It is also a bit of trial and error. There's nothing wrong with putting a coefficient in front of a chemical formula and then actually having to go back and adjust that later. That's fine as well. The only thing is that we can't change these numbers, because that would change the chemicals themselves. All right. So the mole. So the mole is a super useful concept in chemistry, and certainly one that I used a lot in product development. When we're looking at, how much of one thing do you need to for another to react with another thing, or how much of one thing you need to have the same number of molecules as another compound. So a mole is just a way of expressing a quantity of objects. So it's no different to a dozen. A dozen means 12 objects. A mole just means 6.02 times 10 to the 23 objects. So you could have a mole of anything, really. You could have a mole of rocks, but we use the mole in chemistry as the number of atoms in a mole. So 1 mole of carbon has 6.02 times 10 to the 23 carbon atoms in it. A mole of nitrogen has 6.02 times 10 to the 23 nitrogen atoms in it. So it's a really useful way of expressing that. Instead of having to talk about 6.02 times 10 to the 3 every time, we can just say 1 mole of this or 1 mole of that. And you also know that if you had a mole of carbon and a mole of nitrogen and you're bonding them together, so 1 mole, say 1 mole, actually I'll clear that. Clear erase drawings. 1 mole of carbon and 1 mole of nitrogen, then you know that there's enough carbon atoms there to actually bond with all the nitrogens, for instance. Instead of saying, oh, I need 6.02 times 10 to the 23 atoms of carbon and 6.02 times 10 to the 23 atoms of nitrogen, we can just say 1 mole of carbon and 1 mole of nitrogen, and we mean the same number of atoms. And if we have the same number of atoms, then we can figure out what's going to happen when you mix the two together. So another really useful aspect of the mole is to figure out the weight of things. So 6.02 times 10 to the 23 isn't just some arbitrary number that Avogadro, who discovered it, picked out of the air. Actually, it's worked out in such a way that the molar mass is the atomic mass in grams. Okay, so if we go back to the periodic table, so the atomic mass is this number here. This number here. So if we had a mole of fluorine, then that weighs 18.998 grams. If we had a mole of helium, then that weighs 4.003 grams. So it's actually really awesome that we can interconvert them so easily. So 1 mole of a substance just equals the atomic mass in grams. So here we got the example here, iron, the atomic mass is 55.85, so 1 mole of iron is 55.85 grams. All right, so chemical bonding. So in chemical bonding, atoms are coming together to form larger structures. So in order to do this, they need to chemically bond. So there are 2 types of chemical bonds. There's ionic bonds and covalent bonds. And the basis of chemical bonding is the sharing or the transfer of electrons between 2 or more atoms. So ionic bonds result from the transfer of electrons from one atom to the other, as we'll see, while covalent bonds result from the sharing of electrons between 2 atoms. So in ionic bonds, we actually have a transfer of electrons, while in covalent bonds, we actually have a sharing of electrons. So we've sort of discussed valence electrons a little bit. So valence electrons, if I draw that back out again, we had sodium, had 1 valence electron. Oxygen had 6 valence electrons. Carbon has 4 valence electrons. And these are the electrons that are going to participate in bonding. So they're the electrons located in the outermost shell, and they're the ones that are transferred or shared. And usually when we have sort of 3 or less electrons, in ionic bonding at least, we want to give them away. But if you have sort of 5 or more electrons, you want to accept them. So here, sodium's happy to get rid of that electron, because if it gets rid of that 1 electron, it goes back to its octet in the next energy level down for the energy levels of the electrons. Whereas oxygen has 6, so it's easier for it to just get to than actually lose all 6. So another thing to note with the Lewis structures is that if we draw out oxygen again, because I've added some things there, so we draw oxygen. So that's how we've drawn oxygen. So 6. These paired electrons don't participate in bonding, but this one does participate in bonding. So it's only the unpaired electrons that actually participate in bonding. There is a type of bonding called coordinate covalent bonding, which they can share these ones, but that's not really covered in this course. So what we're really looking at is just these unpaired electrons are the ones that are going to participate in bonding. Either they're going to be lost or gained, or they're going to be shared in a covalent bond. Yeah. All right, so ionic bonding. So in the case of chemical bonds between metals and non-metals, as we said, ionic bonds occur. So in ionic bonds, we have a sharing we have a transfer of electrons. So here we've got sodium and we've got chlorine. Sodium has 1 valence electron here, while chlorine has 7 valence electrons. So as we said before, for chlorine, could try to lose all 7 valence electrons, so it can go back to its octet, but that's going to be really hard for it to do, so it's not going to do that. It's going to just want to gain an electron. And sodium as well could try and gain 7 electrons, so it could form an octet, but it's too hard for it to do that as well, so it's going to lose that electron. So that's exactly what we find, is that the sodium ion or the sodium atom gives the electron to the chlorine atom. As we said before, sodium, we always have, protons should equal neutrons, also should equal electrons, sorry. So protons should equal electrons. Because protons have a positive charge and because electrons have a negative charge, when protons and electrons are equivalent, then the charge is neutral. But here, we actually have, 1 more proton now, because sodium has lost an electron. There's 1 more proton. So we express that, so 1 more proton, we express that with this little plus symbol, which just basically means 1 positive charge, so one extra positive charge there because it has 1 less electron. And similarly, chlorine has gained an electron, so it now has more electrons than it does protons, so it becomes a negative charge. And then just like magnets, positive and negative charges attract each other, so the sodium and the chlorine are going to come together and bond ionically. So yeah, so the loss and gain of electrons occurs simultaneously, and then ions with opposite charges attract each other to form an ionic bond. So here we've got sodium and chlorine bonding together ionically, which is of course sodium chloride, which is table salt. So now when we have sodium like this is just the sodium atom, but if we lose an electron and it becomes this positively charged, then we would call it a sodium ion, which just means that it has 1 more or 1 less, or sorry, not 1, but it has more or less electrons than protons. An ion is an atom with more or less electrons than protons. And then clearly it's going to be stable then, because it's lost that 1 valence electron. It's now happy. It's got 8 electrons, 8 valence electrons now. So it has the configuration of a noble gas. So it's now hit that octet rule. And similar with the chlorine. So sodium and chlorine are both happy with that. So they're both more stable as a result of that. All right. So with covalent bonding, what we have is we actually have a sharing of electrons. So way to look at this is we've got water, so that's covalent bonding. So remember that covalent bonding happens between 2 nonmetals. Ionic bonding happens between a metal and a nonmetal. Covalent bonding happens between 2 nonmetals. So here we've got basically, I'm going to draw it like this, just for space. We've got hydrogens bonding with oxygen. Now, if you recall, oxygen has the 6 valence electrons. 1, 2, 3, 4, 5, 6. So that's oxygen. And hydrogen has just the 1. Actually, I'm going to draw it here because that's where I'll draw my little thing. So hydrogen, so ignore that. Hydrogen has 1 valence electron. And then we've got another hydrogen over here with 1 valence electron. So here, instead of actually completely losing that electron, it just wants to share it with oxygen, because we can see that if we put it, if we put it there, then hydrogen's going to be happy, because hydrogen is a little bit different. It doesn't need to satisfy the octet rule because it only has 1 electron. It just wants 2 there. It just wants it to be paired. So those two can share. If it shares the electron with it, then they both can have, they can both satisfy their outer shells. Now, with that covalent bonding, something to be aware of is this sort of polar versus non-polar covalent bonding. So this is just saying that some atoms are a little bit more attractive to electrons than the other one. So in this case, oxygen is called the more electronegative atom. So it really pulls the electron in. So you can imagine that if you had hydrogen, actually I'll just clear the screen. If you had hydrogen and then we had oxygen, and as we said, oxygen has got its little electrons. Now you might imagine that no, I'll clear that. So hydrogen and oxygen. Yeah, you might imagine that because they're sharing these electrons, that spatially, that the electrons are sort of in the middle of the two. So this one's, that one's coming from there, that one's coming from there, and they're both kind of orbiting around. Obviously, hydrogen has this other little electron there. Oh, sorry, no, all that. And they're both kind of sharing those electrons around. But in actual fact, because oxygen is a little bit more electronegative, it likes to pull the electrons towards itself. So what we actually have is we've got hydrogen, we've got oxygen, and that's got its little valence electrons. It's more like, say, that. It's kind of keeping the two electrons more to itself. So hydrogen actually kind of has what we would call like a delta positive charge. That's a little Greek letter delta, because most of the time, it's actually a little bit more positive, because most of the time, it doesn't have that electron very close to it. So it's most of the time, it looks like it has a proton and no electron. So it has a little bit of a positive charge, and that would mean that because the oxygen has the electron closer to it most of the time, it has the delta, and delta just means, a little bit, delta negative charge. So it's a little bit more negative, because although it hasn't completely taken the electron away, the electron is usually pretty close to it. So most of the time, it actually has more electrons than protons. So it's got a delta negative charge. And this is what we call a polar covalent bond, where there's this unequal sharing of electrons. So they're not in the middle like this. They don't kind of equally share them. It's more to one atom. And when it's more to one atom, it's called a polar covalent bond. When it's shared equally, say this wouldn't happen with hydrogen and oxygen, but say these were two atoms that did share the electrons equally, then we call that a non-polar covalent bond. And we're going to see that's very important when we're talking about sort of solubility of compounds. The difference between, why does fat and water not mix together? Well, it's because fat is polar, whereas, water is polar and fats are non-polar, so they don't sort of mix well together. All right. Just one thing to note on that as well with the polar covalent, with the covalent bonds. A bond can be like carbon it's got 4 valence electrons. Now it can form a single bond. It can share 1 electron with another atom. It can share 2 electrons with another atom, or it can share 3 electrons with each atom. So here we're just sharing 1, here we're sharing 2, and here we're sharing 3 electrons. So single, double, or triple bonds are all possible. All right, oxidation and reduction. So the most important thing that I always have in my head when I'm looking at oxidation and reduction is that acronym, which you would have seen. This is OIL-RIG. OIL-RIG. So the O is oxidation, the R is reduction, and it means oxidation is loss, reduction is gain. And that just means that in an oxidation reaction, you're losing electrons, while in the reduction reaction, you're gaining electrons. So if we're looking up here, we've got copper and silver. So here we've got copper has no charge, silver has a positive charge. But then over here, copper has got 2 positive charges, while silver has no charge. So for the copper to go from no charge to 2 positive charges, that means it must have sort of lost 2 electrons, right? Because if an atom loses 2 electrons, then it has 2 more protons than electrons, which means it would have 2 positive charges. Here, silver positive charge, which means it had 1 less electron than protons. But in the end, it actually has neutral charge, which means it's gained 1 electron. So because this one has lost electrons, then it has been oxidized, because its oxidation is loss. So it has lost, so it must have been oxidized. Here, silver has gained an electron, so it has reduction is gained, so it is reduced. Okay. So it's been reduced, whereas this one has been oxidized. And you can see that we told that just by looking at these little charge numbers. So you can actually tell a lot just from the charge. So I know at first oxidation reduction overwhelming, but all you do is you're just looking for these little charges basically, and then just figuring out has the charge gone up or down, and what does that mean for electrons? And then once you know what's happened with the electrons, well then you just use oil rig to figure out what's happened. So one area that does get a little bit confusing is that the thing which is oxidized is actually the reducing agent, and the thing which is reduced is the oxidizing agent. So an easy way to remember that, I suppose, is just that whatever is oxidized, you think the opposite in terms of it being a reducing agent. But another way to look at it is that because reduction means to gain, so reduction is gaining. So here we can see giving electrons over, right? We've said that this is losing electrons and this is gaining electrons. So clearly copper has given electrons over. So because reducing is gaining, copper is giving it to silver. Therefore, silver is gaining it. So copper is reducing silver. So copper is giving it, reducing is gaining. Therefore, copper is reducing silver, if that kind of makes sense. And then similarly with the silver, so silver is gaining electrons whilst copper is losing it. So if oxidation means to lose electrons, then silver is helping copper lose electrons, so it's oxidizing it, basically. And then just noting as well that this is a forward and backward reaction, which means it's reversible. So yeah, so just a couple little things there. So we just figure out the charges. First of all, you figure out the charges, you figure out what's happening with the electrons, is it going up or down, and then you use oil rig to figure out whether it's oxidized or reduced. And then basically it's the opposite. If something is reduced, it's the oxidizing agent, and if something is oxidized, it is the reducing agent. And just noting here that this is not, the charges need to be balanced. So just like you need to balance the coefficients in front here, the charges also need to be balanced. So here we've said we've lost 2 electrons, but we've gained 1 electron. That's actually okay because we've got 2 here. So because we've got this 2 here, that's technically plus 2e, because each silver atom has only gained 1 electron, but we've got 2 silver atoms, so the 2 electrons are sucked up by the 2 silver. So it is still balanced overall. All right, chemical equilibrium. So far, a lot of the time we've been drawing the reactions just with 1 arrow, which means that the reactants are becoming the product. But actually, a lot of the time, we can draw this other arrow coming back, which means that the product can form back to the reactants. So if we just have 1 arrow, then that is a irreversible reaction, so it doesn't go back, and there can be a number of reasons why things don't go back. And when you get further into like nutritional biochemistry and biochemistry, we will see that in making energy from our food, sometimes we can't go back. Sometimes the reactions only go forwards. but quite a lot in our body, reactions do go back as well. And that just means that once the reactants have made the product, well, then the product can go back to making the reactants again. So at first, when you add, say, the nitrogen and the hydrogen in, then there's going to be much more of these reactants than there are going to be of products. There's going to be more reactants than products at first, but eventually, the rate of the forward reaction and the rate of the backward reaction are going to sort of equalize, and eventually, you're going to burn through some of these compounds here. Then you're going to have more of this, and then you're going to have way more. You might have a little bit more of that than this. That's going to be a little bit less, but then it sort of starts to balance out eventually until these rates are equivalent. Then we say it has reached equilibrium when the rate of the forward reaction is the same as the rate of the backward reaction. So anytime that a stress is imposed on that chemical reaction, then the equilibrium is going to be affected. So if we have reached equilibrium, so I'll get rid of that. So we have reached a point where where the NH3 is sort of breaking apart into the nitrogen and the hydrogen as fast as the nitrogen and the hydrogen are making the NH3, then it's reached equilibrium. But if we suddenly chuck in lots of this nitrogen atom, or this nitrogen molecule, then clearly the reaction is going to be a little bit unbalanced. And what the reaction is going to do is it's going to try and ease that stress. And the best way for it to ease that stress is to get rid of all this extra nitrogen. And to do that, it's going to ramp up this forward reaction here until such a time as you actually reach equilibrium again. Because then obviously if we ramp up that, and this is going to increase, which is going to send it backwards a little bit, and then it's going to eventually find its equilibrium. So if we add a product or a reactant, here we're adding a reactant. When we add a reactant, we increase the rate of the forward reaction to clear this reactant. If we were to add more product, then again, that's going to impose a stress backwards. It's going to try and get rid of all this product and go back to just the nitrogen and the hydrogen. So the rate of the backward reaction is going to increase when we add more product until such a time as we eventually get back to equilibrium. If we increase the temperature, so say degrees Celsius, looks like a G, but it's actually a C. If we increase the temperature, then the rate of the forward and the backward reaction increase. And we can see that's going to be the case if you think back to your lectures. When we increase the temperature of something, we increase the motion of the particles, so they're going to be, jiggling around a lot faster. So if we had all these species, all these molecules everywhere, at one temperature they might be sitting around, just kind of gently moving around, and sometimes when they hit, they might react and form, that sort of compound. If we increase the temperature, then these things are going to be zipping around all over the place, and they're going to hit each other a lot more, and you're going to get a lot more products and reactants, basically. So if we increase the temperature, then we're going to increase the rate of the forward and the backward reaction. So any type of stress, the system responds by easing that stress in the best way possible, and that is captured under Le Chatelier's principle, which we learned in our lectures as well. All right, acid-base reactions. All right, so acids and bases are substances that we're going to find a lot when you get further in your studies in nutritional biochemistry and the like. So basically, there's no formal definition of acids or bases. There's kind of two theories that we've kind of learnt. Well, there's one sort of main theory that we've learnt in our lectures, and that's called the Bronsted-Lowry acid-base theory. And in the Bronsted-Lowry acid-base theory, an acid is defined as anything which gives up a hydrogen ion. So anything which is happy to get rid of a hydrogen ion is an acid, whereas anything which is happy to accept a hydrogen ion is a base. Now, a hydrogen ion, H+, is a proton, right? Because if we drew a hydrogen atom, here's our proton, we've got our one little electron zipping around in the cloud out there. If we get rid of that, clearly this now has the positive charge, so that's why we draw it H plus, but we're just left with a proton. So hydrogen ion, H plus, or protons are interchangeable terms. So we're saying that an acid donates a proton and a base accepts a proton. And this is exactly what we're seeing here. So here, with that, we've got hydrochloric acid is becoming the chloride ion, and because it has lost that H, the proton has gone to water to form the hydronium ion, and it's just become chlorine, and hydrogen, and the water has accepted the hydrogen ion to become hydronium. Now, some terms, an acid has a conjugate base. So here, HCl is the acid, and you can see that the chloride ion here is missing the hydrogen, so it is the conjugate base. So the acid has the conjugate base, which I'll say Cb, right? So the acid becomes the conjugate base. And here we've got the base, which is water. So the base becomes the conjugate acid because it is gaining the hydrogen ion, so the conjugate acid. And you can see the difference between the acid and the conjugate base. The acid has the hydrogen ion, or has the proton, whilst the conjugate base is missing the hydrogen. And similarly, the base, has one less hydrogen than the conjugate acid. Now, a strong acid readily gives away its hydrogen. So one way to think about that is the H and the Cl, they don't like each other very much, and they wanna separate. So as soon as hydrochloric acid is in water, that chloride is getting rid of the hydrogen as fast as it can and giving it to water. And so that would be a strong acid because it sort of gives all its hydrogen ion. So you can imagine if an acid is defined as something which donates its hydrogen ion, then something which really readily gives away its hydrogen ion is going to be a very strong acid. It's going to give away all its hydrogen ions to the solution. That's what we see with hydrochloric acid. In the case of hydrochloric acid, once it's given away its hydrogen ion, it becomes a weak base because that chloride ion doesn't want the hydrogen back. And so what we'll often see is that the reaction is just drawn with one arrow pointing forward. It doesn't really want to go backwards. It's not really reversible. It just wants to give away all its hydrogen ions, and once it's done that, it's happy, it's stable. A weak acid, weak base, is a little bit different. So here we've got this hydrogen fluoride. Hydrogen fluoride is quite happy together. The hydrogen and the fluorine want to stick together. So when you put hydrogen fluoride into water, maybe a little bit of hydrogen goes off and becomes the hydronium ion. And as a result, the fluorine is left on its own, but it doesn't really want to do that a whole lot. And once it has done that, well, the fluorine is a little bit uncomfortable sitting out here all by itself. It wants the hydrogen ion back, so it will quite quickly go backwards. So here we say a weak acid becomes a strong conjugate base. So the weak acid, it's weak because it doesn't want to give the hydrogen ion away. If you mix that in water, the whole thing doesn't become very acidic. However, the fluorine is a very strong base because as soon as you put fluorine near anything that has hydrogen, it's going to want to, or at least put it with hydronium ion, it's going to want to pull that hydrogen back to itself to become its weak acid again. And because of that, we draw it both ways, so we can say that it's reversible. Now, so that's one way of telling a strong acid from a weak acid is that in a strong acid, the reaction will just be written, with an arrow pointing to the right, whereas a weak acid will be written reversibly. Okay, so buffers, again, buffers extremely important compounds in our body. So basically, one of the reasons that we don't want our blood or any sort of intercellular, like the cytosolic fluid, to become too acidic or too base is that proteins, which make up enzymes, transporters, and do lots of things in our body, they need to exist at a certain pH. So as soon as we change the pH of our blood or our cell medium, then those proteins can actually sort of fall apart. And then if they fall apart, well, we're in a lot of trouble. So the our body wants to keep the pH of our blood and the pH of our interstitial fluid and all the rest of it, wants to keep it within a very narrow range. So blood here, we've got 7.35 to 7.45 is the pH range. So the way that our body does that is by using a buffer. So a buffer is an aqueous solution, so like a watery solution containing substances which prevent the major changes in the pH when small amounts of acid or base are added to it. So typically, it has a weak acid and a strong conjugate base, or it has a weak acid with its conjugate base. So you can see here in the blood, we've got this bicarbonate carbonic acid buffer system, where essentially, we've got the weak acid here. We might add that in. It donates to the hydroxide ion to become this basically. So the hydrogen goes over, so we can see that the hydroxide ion becomes water, and this obviously has less hydrogen in front of it as well. So it's just a weak acid being neutralized when you add it. So if you add a small amount of added base in, this will, if you add a small amount of base into this reaction here, this compound will donate its hydrogen to it to neutralize it. Conversely, if you add acid in, then this compound is going to accept the hydrogen to become carbonic acid, CH2 here, and water. So either way, it doesn't matter whether you add a base or an acid, this bicarbonate ion is going to accept, is going to either donate its hydrogen ion to clear it, or it's going to actually accept a hydrogen ion to clear the acid. And then because this is a reversible reaction, you're able to actually find equilibrium between these two states. So you can clear added base or added acids. And this finally, the saturated, unsaturated. So this is not on the quiz this week, so just really, really quickly. When we get to organic chemistry, we're really interested in functional groups. So functional groups are the component of a molecule which give that molecule a lot of its chemical properties. So in alkanes, basically we're talking here about hydrocarbons, so long chains of carbon and hydrogen bonded together. In an alkane, we just have single hydrogen bonds, so single hydrogen bonds. In an alkene, we have a double bond somewhere in the molecule, so it might look like that. In an alkyne, we have triple bonds, triple bond there, then back to double bond or single bonds, for instance. So saturated, so the difference here is that this is a saturated hydrocarbon, whereas these are unsaturated hydrocarbons. And what we mean by that is just that a saturated hydrocarbon has the maximum amount of hydrogens. So with this molecule here, we have C, C, C. You can imagine that these all have H's, hydrogens here. So if you were to draw all them out, you see that you've got the maximum amount of hydrogens there. If we added a double bond in there, we said C, double bond C, because carbon can only have four bonds, then whilst this one has the single bond there, and therefore it needs 3 hydrogen bonds, if we put another bond in here, then it only needs 2 hydrogens. And similarly, if we drew that triple bond there, then it only needs 1 hydrogen atom there. So it's got the least amount of bonds. So yeah, saturated versus unsaturated basically just differ in terms of how many hydrogen atoms they have. And saturated hydrocarbons have the most amount of hydrogen atoms, whilst unsaturated hydrocarbons have less hydrogen atoms because the carbons already don't need as many to sort of bond with. All right, so that went a little bit longer than I expected, but do we have any questions? It's a bit hard to ask, but if you want to type your question in, I can see your chats here. So does anybody have any questions? Oh. Sorry. Go to questions pane. Oh. All right. Okay. So is it so someone has asked, so is the atomic mass always measured in grams or just when relating to the mole? So just when relating to the mole, so atomic mass is typically in atomic mass units or AMUs. It's just that 1 mole of how do you put it? Sort of the 1 gram is equal to 1 atomic mass unit. So yeah, so atomic mass, the actual unit for atomic mass is AMU or atomic mass unit, but it's just that we can use it to we can easily convert between atomic mass units in grams when we're talking about molar quantities. So hopefully that answers that question. So yeah. Format of quiz. So format of quiz. Might have to get back to you on that. If so, whoever asked me or Rommel, who the format of the quiz. So it's obviously multiple choice questions. So there'll be, I think there's like 30 questions, 30 multiple choice questions that are just going to be on the weeks 1 to 3 content. If you have a more specific question about the format, yeah, just message me or post it in the loop and I'll be able to find the answer to you. Hopefully that answers your question though. I think it's about 30 questions for 40 minutes, all multiple choice. Yeah, so all multiple choice questions as far as I'm aware. I'll double check that if it's not multiple choice, I'll quickly post a note up on the loop, but yeah, I'm pretty confident that it's all multiple choice questions. Does anybody else have any questions? Okay, I see what you mean. So yeah, all multiple questions, 10 questions for each week, roughly. You know, I don't know the answer to that question. I will check for you to see if that's an answer that we can give. I'm not sure whether how much detail they like to provide about the quiz, but I can ask whether. Yeah, I'll ask for you. Oh, good. Thank you very much, Cassandra. I'm glad to be of help. And as I said, if anyone has any other questions at all, just message me or anything like that, and we can talk through it. Oh, thank you very much, Karen. Cool. Well, that's it. Looks like that's all the questions coming through. So that webinar will be put up if you want to watch it again. Otherwise, we can always chat outside of that. Otherwise, you can all go about your day and good luck on your quiz. No worries. Thank you. Bye.